take a look at how to calculate an acid dissociation constant for a weak acid. I've got propanoic acid here. I know it's a weak acid because it's an organic acid. If I see hydrogens and carbons hooked together in an acid, I know it's weak. So I can't just do negative log of the concentration. It does not work because most of the propanoic acid does not dissociate. So what I'm going to do here, however, is I'm going to still use my ice table, and I'm going to fill in what I know. I know that my initial concentration of propanoic acid is 0.010, and then all the other information I have is a pH. And when this reaction comes to completion, which is very quickly, the pH of the solution is going to be 3.43, so that's going to give me the equilibrium concentration of hydrogens. So I can find what those are. I can go ahead and say that the pH is 3.43. And I can back that up and reverse this process by saying 10 to the negative 3.43, which is the antilog, is going to be the concentration of hydrogens. And when I put that into my calculator, I find that my concentration of hydrogens is 3.72 times 10 to the negative fourth. And that's going to be the concentration of hydrogens at equilibrium. 3.72 times 10 to the negative fourth. So this is the information that I have currently. I'm going to erase this pH business because I need the room. And I also can figure out some other things because I know that equilibrium must shift to the right, because when I throw the propanoic acid into water, I have to break it up into its ions. So with that being said, before I do that, I have no propanoate. I have no hydrogen ions. I know that I am in a 1:1:1 ratio. So I'm going to lose some amount of moles of my propanoic acid, and I'm going to gain the same amount here and here. And again, since I'm in a 1:1 ratio, I know that this also has to be 3.72 times 10 to the negative fourth. So I can clearly see what X has to equal here. X has to equal 3.72 times 10 to the negative fourth, because I've got 0 plus X equals this. So now I'm ready to figure out my equilibrium concentration of propanoic acid. So I can say 0.010 minus the 3.72 times 10 to the negative fourth. And I'm going to type that into my calculator, 0.010 minus 3.72 times 10 to the negative fourth. And I find that I end up with 0.0096 moles per liter of the propanoic acid left. Barely any of it has dissociated, hardly any. And that makes a lot of sense because once again, I've got a weak acid. So now I'm all ready to go to get my Ka value. So to get my Ka value, I set up my equation. I'm going to have my concentration of what I call propanoate, which is CH3CH2COO minus my concentration of hydrogens all over my concentration of the propanoic acid. Now I'm ready to fill in my values. So my values here, I'm going to have a 3.72 times 10 to the negative fourth And so is this one here, the hydrogen concentration. So I'm just going to square that all over 0.0096. So I'm going to take a moment and type that into my calculator. And when I went ahead and typed that into my calculator, you might have heard a brief pause. I didn't want to pause so long while I did that. I get 1.44 times 10 to the negative fifth. So I'm going to also show you my units for this. This is moles per liter squared. This is plain old moles per liter. Hope you love the train in the background. That moles per liter cancels out. The squared cancels out. It's 1.44 times to the negative fifth moles per liter. And you could actually look up the Ka value for this on that chart I gave you or in your IB data booklet that's in the nuts and bolts folder, and you'll see that's a lit value for propanoic acid. Not that you know what propanoic acid is right now, just know it's a weak acid, and all of these weak organic acids are going to end up with an exponent that is around 10 to the negative fifth. All right, so here's the Ka example for